Hey everyone, so we're on to the second part of this modern physics topic, which is all about subatomic particles. Um, Now, we already know that when we have the atom is essentially the smallest structure of any type of matter, and that atom is made up of a dense nucleus, which it has protons and neutrons, and then there's these even smaller particles, the electrons, that float all around it. They orbit in these electron clouds of probability and such. One thing to note is you're going to learn. You're going to have to answer this question. The protons and neutrons are actually held together in the nucleus by the strong force. So, as we learned in electrostatics, protons don't want to be near each other. Positive charges don't like being so close. Normally, if we put two positive charges in a close space, they'll repel. So it turns out that there's got to be something that's counterbalancing the electrostatic repelling force in order to keep these protons inside the nucleus. And it turns out that that's what we call the strong force. Now the strong force only acts in a very limited range. It's a very short range force. Therefore, in order to create fusion between two particles, which we sometimes do, one of the things that we have to do is actually try to overcome the electrostatic force by essentially accelerating these positive protons towards the nucleus and trying to bombard it with such a fast speed and so much energy that the even with the repelling force of the electrostatic force, it's still able to get just close enough to overcome it, and which the strong force takes over and actually absorbs it into the nucleus. So this is actually leads into something I didn't write it in here, but there's four main forces. There's four fundamental forces. They're called. We've actually already learned about three of them. So the first one is the gravitational force. So the force between any massive objects that pretty much brings it all together. The second is the electrostatic force. So this is based off of charge. The third force is the strong force, which is what keeps the nucleus together, the protons together. And then the fourth one is called the weak force. You might have learned about this in chemistry. The weak force is actually what's in charge of beta decays and stuff like that, or any sort of radioactive decay where the nucleus just kind of releases particles and changes elements. So these are the four fundamental forces, and the main goal of scientists is to try to find a way to combine them together. As it turns out, a lot of these forces kind of don't really work in a lot of similar cases. It's very hard to kind of switch between one or the other, or like we don't really know why some exist and how they could affect others. So the big goal for scientists is to try and find a way to combine them all together into one. Um, Sometimes that's called the grand unified theory, which is combining all of this together, combining the relativistic mechanics of large scale bodies and quantum mechanics from the small scale bodies all into one nice packaged description of the universe. So the protons, the neutrons, and the electrons are all really small particles. So like the radius of an atom is on the scale of 30 to 300 picometers, which is 10 to the negative 12. Protons are about 0.85 femtometers, which is 10 to the negative 15. Electrons are even smaller at 10 to the negative 20. A lot of times in science, we kind of consider electrons as being, infinitesimally small points in space. So it turns out that maybe there's nothing smaller than that because those are all extremely small particles. Never would we ever be able to see them with anything other than some sort of electron microscope. So there can't be anything smaller. Well, turns out that there are. There are actually subatomic particles. There are particles even smaller than that. However, One thing to note is that even though we have these subatomic particles, they are completely unstable by themselves. So a lot of the stuff that we talked about in electrostatics, like the fact that we can only have whole number charges and that the electron is essentially the smallest negative charge and the proton's the smallest positive charge, that's still true because technically these subatomic particles, which carry fractions of these masses and charges, don't exist by themselves naturally. Pretty much we have to go through very extensive particle acceleration in order to create them. So we ended up discovering this through our better technology by taking particles, accelerating them to near speed light, and slamming them into each other, and noticing that we actually did get fractions of charges. Now, these subatomic particles, the protons and neutrons actually were made up of subatomic particles. They're called quarks. So those little tiny pieces that make up the protons and the little tiny pieces that make up neutrons, we give them a special name called a quark. Now, it actually is turns out that the electron still is not made up of anything. So that still kind of holds true that the electron, as far as I know, is still pretty much the smallest possible particle. But it turns out protons, neutrons, and some of the other particles that we have uh, can be broken down a little bit further. So quarks are really, really tiny particles, and each quark has their own special name. It carries a fraction of the charge that makes up these bigger particles. It also carries a fraction of the total mass. And there's also different generations of quarks, which I'll mention in a second. So this is actually a list of all the different types of particles, basically, all the subatomic particles. So in the purple, you have what we call the quarks. There's up and down quark, the charm and strange quark, and top and bottom quark. So these are, they're actually combined into what we call generations. This is the first generation, the second and third, but you don't need to worry about that. In the green, we have particles that don't get broken down any further. They're actually the smallest possible that exist. We give them a special name called leptons. This includes the electron neutrino, muon neutrino, tau neutrino, electron, muon, and tau. Not going to go into any detail with that stuff, but you'll notice that the electron is part of this lepton. And then there's these gauge bosons, but you don't need to worry about those. Now, that's a lot to take in. So, do we have to know all that? Not really. In the reference table, you're going to be given this diagram. I think you also are given the bottom part of this with the leptons, but you're going to be given this with all the quarks. So again, there's six quarks, all with their own special symbol. So U for up, C for charm, T for top, D for down, S for strange, B for bottom. And one thing that's really nice for you to notice is that the charge that's on the quarks are all consistent. So all the positive terms, up, charm, and top, are given positive charges, plus 2/3, plus 2/3, plus 2/3. And then all the negative sounding traits, down, strange, bottom, are given negative charges, negative 1/3, negative 1/3, negative 1/3. Notice that there's this E there. This goes back to the electrostatics. E is 1.6 times 10 to the negative 19 coulombs. So this is saying that it's 2/3 of this original value. This is that smallest possible charge. So this is 2/3 of that. All right. So we have what we call the classifications of matter. So we have matter, and matter can be broken up into two different parts: hadrons and leptons. Leptons can't be broken down any further. That's what they are. Um, Electrons are leptons. They're indivisible. This also includes the neutrinos and positrons. Hadrons can be broken down into further categories. The two other categories would be baryons and mesons. Baryons are made up of three quarks. So if you go to that table and you pick three quarks, that's a baryon. Mesons are made up of a quark and an antiquark. I'll explain what an antiquark is in a second, but that's what a meson is. It turns out protons and neutrons are considered baryons because both of them are made up of three quarks. All right, so here's the next question. Try to figure out the answers. Pause the video, work stuff. I'll go over in a second. All right, so here it says that protons and neutrons are baryons. So again, there's three quarks, and I need to make up them so that we get +1 and 0 for the protons and neutrons, and they can only be made up of ups and downs. So for a proton, since it's a baryon, we know it's got three quarks. Now the quark combination, if I look at the chart and I try and think about how I can combine three combinations of ups and downs, the only configuration that will get me +1 is up, up, down. Sometimes that would be rewritten as U, U, D. And that's because if I take this, I take the 2/3 plus 2/3 minus 1/3. I end up with 3/3, which is +1. And then down here, what configuration makes up a neutron? Up, down, down. Again, if I look through this, this is +2/3 minus 1/3 minus 1/3. And that gets me 0. You're actually going to need to remember these for the regions or the final test that we're going to take. So protons are up, up, down. Neutrons are up, down, down. Again, if you just remember that they're part of that first generation, they're the main particles, so they're going to be the main two. You can figure this out on the test by just, seeing what combination of ups and downs give you +1 and what combination of gets you 0. All right. Here's the next question. Pause the video, work yourself, and we'll go over in a second. All right. So they say a deuterium nucleus is one proton, one neutron. Deuterium, if you didn't know, is a isotope of hydrogen. So this is a hydrogen atom that has an extra neutron. So protons we already found have up, up, down, and neutrons are up, down, down. So if we combine them, a deuterium nucleus will have 3 ups and 3 downs. That's pretty much it. All right, here's the next question. Pause the video, work itself. We'll go over a second. All right, so they want to know which particle would be unaffected by an electric field. So what we want to do is just, even without reading what this actual question is asking, let's just figure out what the charge is. So charm, strange, strange, that's +2/3, minus 1/3, minus 1/3. This has a total charge of 0. Bottom, 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 that's minus 1/3, minus 1/3, minus 1/3. That gets me -1. Up, down, charm, that would be +2/3, minus 1/3, +2/3. That gets us +1. And then up, up, down would be +2/3, +2/3, minus 1/3, which gets me +1. So clearly, choice C and D have to be taken out because both of them have the same charge, +1. So they want to know which one would be unaffected by an electric field. So that means that we're looking for something that isn't affected by the electrostatic force, essentially. Which one wouldn't be attracted to or repelled by a positive object or a negative object? The only one that makes sense is A, because that one's neutral. Neutral objects are not attracted to charged objects. All right, here's the next question. Pause the video, work itself. I'll go over in a second. All right, here we have 3 quarks making up this lambda particle. So what would it be classified as? We look at the reference table. We look at that chart of the classification matter. The only one that fits the bill is the baryon. Remember, the meson's made up of 1 quark and 1 antiquark, so essentially 2 subatomic particles. This is made up of none. This is just like itself. And photon is just a form of light. All right. So this leads into something called antimatter. So one of the things that we found was that it actually turns out that each particle, each subatomic particle, everything has what you can consider almost like an evil twin. And that's what we call antimatter. So antimatter are particles that have identical masses but different charges. Now, for example, protons and electrons have different charges. They have the exact opposite. Protons are positive, electrons are negative. But they are not antimatters of each other because the proton, if you look on the reference table, has a mass of 1.67 times 10 to the negative 27, while electrons have a mass of 9.11 times 10 to the negative 31. Those masses are completely different. So they are not antiparticles of each other. So for the anti-electron, what we'd want is the exact same mass of 9.11 times 10 to the negative 31, but the charge is opposite, plus 1. An anti-electron actually has a very common, because it's one of the more common forms of antimatter, it actually has the name called a positron. So if you ever see that word, that's referring to anti-electrons, antiparticles of electrons. Normally, what we do is we give them a bar above that symbol to represent the anti version. So electrons can sometimes be given the symbol E to represent electron. Positrons are given E bar to represent the antimatter electrons. Quarks, same thing. You know, if we have an up quark with a U, put a bar above it, that's an anti-up. So that'd be the antimatter quark. So going back to what we talked about with mesons, what you're going to have to do is pick one quark and one anti-quark and combine them together. However, you cannot combine the same type. So you would not be able to combine an up with an anti-up, as you'll see in a bit. All right, so here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so we have an antibaryon that's made up of two anti-ups and one anti-down. So again, remember, anti-ups have the exact opposite charges. So what I can do is I can look at what would it be if I had normal particles, normal quarks. So instead of looking at two anti-ups and two anti-downs, I could just look at two ups and two down and one down. So up, up, down is actually a proton, which is plus one. So anti-up, anti-up, anti-down would be negative one. You could have also remembered that since up is plus 2/3, anti-up would be minus 2/3. So this becomes minus 2/3, minus 2/3, plus a third because of the anti-down. And that's where we get the negative 1 from. All right. Here's the next question. Pause the video, work itself. I'll go over in a second. All right. So they want to know what all these particles are classified as. Since all these particles have 3 quarks in total, we know that they are all baryons. Now they want to know which particle has the opposite charge and is more massive than a proton. So we need opposite charge. So we're looking for something that's negative. So this one's out, and then these two are out. And then they want more massive than a proton. Now a proton is 0.938, as they said here. This antiproton has the exact same mass, so the answer is the omega particle. The omega particle has the opposite charge, but is more massive than a proton. One thing to note, I'll mention this very quickly, but there actually is an altered unit for mass. Instead of dealing with the actual mass in kilograms, because that's such a small number, what they do instead is they use this unique unit, which is giga electron volts per speed of light squared. I'll briefly mention that later. All right. So going back to what I said before about how you can't put an up and an anti-up together. You can't put a particle and its antiparticle together because what happens is when they come in contact, they actually annihilate each other. They completely destroy each other and turn all their mass into energy. So the amount of energy that gets released is equals mc squared. So now you've probably finally learned what this equation is all about. If you've ever said it jokingly or if you've seen it, now you know what it means. It's the equation that tells us how much energy we can convert from a form of mass through this type of setup. It also helps us go the other way, as I'll mention later on. All right, so here's a practice question. So pause the video, work itself. We'll go over in a second. All right, so here we have the two particles coming together. Now, both Mr. Clow and anti-Mr. Clow have the same mass of 110 kilograms. So when they annihilate each other, we're going to have to combine their total mass together. 220 kilograms of energy are being converted, or sorry, 220 kilograms of mass are being converted into energy together. So we do that, multiply it by the speed of light squared, and we get 1.98 times 10 to the 19 joules. So just to put this number into perspective, that is more than the yearly electricity consumption of the US since 2009. So this amount of energy is what is released or used up by the US throughout an entire year. This would be released within a fraction of a second through this antimatter annihilation. Another thing to point out is that this is 100 times more powerful than the 50 megaton Tsar bomb, which I should note is 27,000 kilograms. So my 220 kilogram matter antimatter annihilation is 100 times more powerful than something that weighs about 100 times heavier than it. So, interesting point. It's actually because of this, a lot of scientists really want to find a way to harness matter antimatter annihilation as a form of energy, as a form of weaponry, as a form of space, like traveling through space. It's a very, very important aspect in the field of science. Problem is, it's really hard to create antiparticles. I shouldn't say it's really hard. It's expensive to create antiparticles, and it's really expensive and hard to capture and keep them suspended so that they don't annihilate themselves. All right, here's the next question. Pause video, work stuff. I'll go over in a second. All right, so we want to know how much energy is released from the electron and anti-electron. So this is pretty much, you can think of this as being like the smallest form of the energy conversion. So again, both the electron and positron have the same mass, so we have to double that to figure out the total mass being converted. Plug that in, and we get 1.64 times 10 to the negative 13 joules. So very, very small. But that's only an electron, a very, very small particle. Here's the next question. Pause the video, work stuff. We'll go over in a second. All right, so same thing. Both objects have a 5 kilogram mass, so double it, and we get 9 times 10 to the 17 joules, or about 4 Tsar bombs. So again, if we get a kilogram of a part of any amount of antimatter, we can get an extreme amount of energy released from the annihilation. Here's the next question. Pause the video, work stuff. I'm going to go over in a second. All right, so here, this is actually one of the interesting things. If you've ever heard the statement that matter cannot be created or destroyed, or that energy cannot be created or destroyed, technically those are half truths. We can create mass, we can lose mass. We can create energy, we can lose energy. The thing though is that because of this equation, they're forever linked together. So if we lose mass, it has to have it means that we have gained that amount of energy in the process. So this missing mass has been converted into energy. Quick side note: this is actually a form of Hawking radiation. Essentially, energy that gets emitted by black holes is usually caused by particles, protons and antiprotons being created outside of the black holes, and then one of the particles actually being absorbed while the other one kind of floats off into space. It's also happens in a lot of reactions where we take two particles, slam them together, and a lot of the excess energy from the collision is used to create new particles, uh, essentially out of nothing. So this is what I said before. Yes, we can create energy sorry, we can create mass from energy if we have enough of it, um, and it uses the exact same equation. And it's actually one of the reasons why if we take a proton, we take an antiproton, and we slam them together rather than just letting them, touch and annihilate each other, we can actually create a particle that has 6 times more energy and more mass than before. Now, the one thing to note is that when we do this, if we do create matter from energy, like from nothing, we just like how we had to create the energy using particle antiparticle annihilation, the same thing applies the other way. So if I want to create matter from energy, I have to once again I have to create particle antiparticle pairs. This means that if I slam particles together, I cannot just create a proton. I create a proton and an antiproton, or I create an electron and a positron. So this comes from the conservation of energy. That energy cannot not energy charge cannot be created or destroyed. So that one still holds true. So if I create a negative electron, I have to also create something positive that kind of counterbalances it, and that's the positron. So very quickly, I'll try to finish this up. As I said before, kilogram is way too big for subatomic particles, so we have other units that we use for it. One of them is the AMUs, the Universal Mass Unit. That one you've probably seen in chemistry. On the front of the reference table, there's a conversion to find how many AMUs is a kilogram. Essentially, it's the mass of a proton. So the amount of AMUs is essentially asking you how many times bigger or smaller is it compared to a proton. So a proton is 1 AMU, neutrons are 1 AMU, so on, so on. So if you see that, it never goes into an equation. It's just a conversion. And that's a conversion that you're going to use um, based off of the reference table equation. The second alternate unit is called the energy mass equivalent unit. On the reference table, you'll see it as MeVs per c squared. Essentially, it's telling you how much energy you would get from an annihilation through the E equals mc squared equation. That's actually why the c squared's in here. It's kind of a little bit weird. Um, Protons have a mass of, so we would say that protons have a mass of 938 mega electron volts per c squared. This basically means that we would get 938 mega electron volts when it gets annihilated. So that's kind of the main gist and thing that we like about this equation is that it can be used in conjunction with the E equals mc squared very, very easily. And that's it. If you have any other questions, feel free to let me know. Otherwise, good luck, and I'll see you later.